2, and it ends at time t minus 1. And here, the second leg, because it's lagged 2 time units, we start at time t is 1, yeah, and it ends at time t minus 2. So in the same manner, if you have more legs here, it's straightforward how this have to look like. Yeah? So this matrix here is then t minus 2 by 3. Yeah? Of course, it must be like that. So our beta vector is then simply defined as delta 0, delta 1, delta 2. Very simple and straightforward also. Our vector of regression residuals here, it's obviously defined as a t by 1 vector. So we start at observation e is 1, e is 2, until e is capital T minus 2. So that's also it, t minus 2 by 1 vector. Yeah? That's a t minus 2 by 1 vector, like our y. So now we have set up our model, very simple. So then we get our beta hat is then obviously given by x transpose x minus 1 x transpose y, yeah, using these input matrices. Yeah? So then we get the regression residuals, now denoted as, let's denote them as E hat. So our regression residual vector is then simply given by y minus x times beta hat, yeah, using our estimates and our defined data matrices. Yeah? We get the estimated regression residual vector. So we need this vector obviously for setting up in the fourth step and the test statistic. For implementing the test, we need the R squared, which is the coefficient of determination for this auxiliary regression. Yeah? So using this, our R squared is defined for that equation is defined as 1 minus our estimated residual vector transpose times itself divided by the variation of our dependent variable, yeah, this guy here. So we can estimate this very simply. We are using this formula here, yeah, and then the final step is then that our test statistic lambda is distributed as t times r square, and under the null hypothesis our test statistic lambda is distributed as chi square with 2 degrees of freedom. Yeah? It's asymptotically distributed as chi square with 2 degrees of freedom. Yeah, and again, t is the number of our observations. Yeah? And because it's asymptotically distributed, you can always argue, okay, it should be t minus 2, right? But in asymptotics, it's the same, obviously, so it doesn't matter. All this is based on asymptotic theory. And we assume that t is very large. Of course, in practice, in real life, t is obviously limited. It's not infinite, but this is based upon this asymptotic theory. Yeah? And then again, we have our test statistic. Yeah? Let's take this away. In this arch LM test under the null hypothesis A0, there are no arch effects, which means obviously that our process looks like well behaving. Yeah. Which also means obviously that our delta 1 is 0 and our delta 2 is 0 in this case, yeah, because obviously we don't have any autocorrelation in the squared residuals of the mean equation. And under the alternative hypothesis H1, we have arch effects. There are arch effects, which means obviously then we have this volatility clustering. This volatility clustering is significant. Yeah. Which also means then that delta 1 is unequal to 0. It's actually larger than 0 because obviously the volatility, this guy is larger than 0, and also the second guy, or the second guy is larger than 0 as well. Yeah. So, and again, the chi-square distribution, how does this distribution look like? Well, we know this from the statistics classes. It looks a little bit like this. Yeah. And then we have, of course, we have to check what is the value for the 95% probability. Yeah. If you have a significance level of 5%, yeah, if you want to have 5% here on the right tail, then we have obviously 95% here. Yeah. And the critical value divides our 95% from this 5% quantile, or from this 5% probability mass. So whenever our test statistic lambda that we estimated here falls into this area here, which is beyond the critical value for this 95% probability, then we reject the null hypothesis, which implies we have arch effect in the data. Whenever this test statistic is below, within this area here, below the critical value, then we obviously do not reject the null hypothesis. Yeah? In this case, we assume that our data is well behaving, and we do not need to model the second moment separately. Okay. This was the erratum that I wanted to discuss with you. And now, once we have found that we have arch effects in the data, now the next question that arises is, okay, how do we model these arch effects? So the topic that we have now is simply arch or GARCH modeling. Yeah, my handwriting style is terrible. Simply GARCH models, arch models. So let us start again with the mean equation. Let's denote our exact returns of our assets as usually as yt. And we have an intercept term alpha, and we have an error term as denoted as epsilon. Yeah? So that's the mean equation. And of course, depending on our model, or depending on what we want to do, depending on our research question, this mean equation can look very differently. Yeah? We can have here more regressors, different regressors. We can have lagged dependent variables. It depends on the model. Yeah? But let's assume that we are now interested in only modeling the volatility dynamics of that single asset. Yeah? And we assume there's nothing else that has an impact on that asset. So then we have a second equation where we model the conditional volatility. Yeah? So this guy here, this error term, is defined as sigma t, which is the conditional volatility at time t. Yeah? It's now time varying. This guy is time varying. This guy is time varying because this guy is time varying, times et. Yeah? What is et? ET is the random part. That's the random part. And different textbooks give you different notation, so don't get confused, right? This can be epsilon, xi. People have different opinions about that, or different like notations that it's here, it's just ET, but this is the random part. And ET is basically the process that is random. Yeah? That's our random component. So an ET is assumed to be, usually ET is assumed to be normally distributed with zero mean and variance 1. Okay? So sigma t, which is the conditional volatility, is given by the square root of what? W0 plus sum from I is 1 to capital P W times Wi epsilon squared T minus I. Yeah? So that's the general formula of an arch model. And about GARCH model we will talk a little bit later. Yeah? So once again, what you see is obviously that this guy here is a function of path squared residuals from the mean equation. Yeah? And it's defined here as the square root of this function. Yeah? W0, this measures basically, this is the unconditional volatility. Yeah? It's obviously because it gives the level of volatility when all of these Wi's, legs, yeah, from I to capital P are 0. So and again, so how do we choose the perfect P? Again, there's no rule, obviously. So you have to have some assumption. And some people, again, they check the autocorrelation function of the epsilon. But of course, you have to start somewhere. Yeah? So basically this guy here, we can also see it or consider it as the square root of epsilon t squared. The square root of epsilon t squared. So this guy squared and then taking the square root out of it again. Yeah? This is basically how we can look at it. So now first, how do we define our model? So first of all, we have to get straight with the mean equation. So our y vector is again given by y1, y2. So we have the time series observations in a t by 1 vector. Yeah, here we have our X matrix. It's now simply just a vector of ones. Yeah, it's obvious, just a vector of ones, the simplest case we can think about. So then we have obviously that our beta hat is the same as our alpha hat. It coincides because it's just one value, one scalar, and it's given by x transpose x inverted x transpose y. Okay. Given our simple point estimate here for the intercept term, we can define our vector of mean equation residuals as epsilon hat equal with y minus x times alpha hat. Very simple. So now we have our vector of regression residuals from the mean equation. Let's take this away. So let's say we have P is 5. So we assume that we have a dependency structure of 5 legs here in the volatility process. So our regression equation for the second moment, for the conditional volatility, would be then obviously epsilon hat squared. Yeah, think now again, this guy here is actually our epsilon t squared. So this is our epsilon hat, or estimated epsilon t squared is equal with, so we have to basically, we square now this equation here on both sides. This becomes sigma t squared, which is the same like epsilon t squared, and here the square root disappears. Yeah, because we have to do it obviously, otherwise we cannot run the regression equation. So epsilon t squared hat is equal with w 0 plus w1 times epsilon t minus 1 squared plus w2 epsilon t minus 2 squared plus, and so on, until we end up with w5 times epsilon t minus 5 squared plus epsilon, or top like this t, which measures our regression residual. So now we translate our regression model